Going carbon negative. What are the technology options? Site commentary. What is the difference between carbon neutral and carbon negative? Microsoft recently announced that it aims to become carbon negative by 2030. What's more, the company said that by 2050, it plans to have removed from the atmosphere all the carbon that it has emitted since it was founded in 1975. This is a significant commitment from an individual company, and it underscores the potential for approaches using negative emissions or carbon dioxide removal to play an important role in meeting international climate goals. Carbon neutrality, or net zero, means that any CO2 released into the atmosphere from human activity is balanced by an equivalent amount being removed. Becoming carbon negative requires a company, sector, or country to remove more CO2 from the atmosphere than it emits. Meeting ambitious international climate goals may require global CO2 emissions to fall below zero in the second half of the century, achieving what is known as net negative emissions. In the Intergovernmental Panel on Climate Change, IPCC, Special Report on Global Warming of 1.5 degrees Celsius, published in late 2018, almost all the pathways analyzed by the authors relied to some extent on carbon removal approaches in order to achieve net negative emissions after 2050. This does not mean, though, that carbon removal is only a long-term solution. The technologies can also play an important near-term role in clean energy transitions. They can neutralize or offset emissions that are currently technically challenging or prohibitively expensive to address. This includes in some industrial processes, such as steelmaking and cement production and long-distance transport, like shipping and aviation. It is important to note that carbon removal technologies are not an alternative to cutting emissions or an excuse for delayed action. But they can be part of the portfolio of technologies and measures needed in a comprehensive response to climate change. How can CO2 be removed from the atmosphere? There are multiple ways of removing CO2 from the atmosphere, most of which fall into three broad categories. 1. Nature-based solutions. 2. Measures that aim to enhance natural processes. And 3. Technology-based solutions. Nature-based solutions include afforestation and reforestation. These involve the repurposing of land use by growing forests where there was none before, afforestation, or reestablishing a forest where there was one in the past, reforestation. Other nature-based solutions include restoration of coastal and marine habitats to ensure they continue to draw CO2 from the air. Enhanced natural processes include land management approaches to increase the carbon content in soil through modern farming methods. This can incorporate the addition of biochar, charcoal produced from biomass, to soils, where the carbon can remain stored for hundreds or thousands of years. Less developed approaches include enhanced weathering to accelerate natural processes that absorb CO2, for example, by adding very fine mineral silicate rocks to soils, or ocean fertilization in which nutrients are added to the ocean to increase its capacity to absorb CO2. Enhanced weathering and ocean fertilization approaches require further research to understand their potential for carbon removal as well as their costs, risks, and trade-offs. Technology solutions include bioenergy with carbon capture and storage, BCCS, and direct air capture, which, as the name suggests, involves the capture of CO2 directly from the atmosphere. Both of these solutions rely on geological storage of CO2 for large-scale carbon removal and could play an important role in clean energy transitions. They are discussed in more detail below. In pathways limiting global warming to 1.5 degrees Celsius with limited or no overshoot, the IPCC found that agriculture, forestry, and land use measures could be removing between 1 billion and 11 billion tons of CO2 per year by 2050. The potential amount of CO2 removal from BCCS ranged from 0 to 8 billion tons per year by then. To put this in context, global energy-related CO2 emissions were 33 billion tons in 2018. Other carbon removal options are not included in the IPCC pathways because of their lack of maturity. Bioenergy with carbon capture and storage. BECS involves the capture and permanent storage of CO2 from processes where biomass is burned to generate energy. This can include power plants using biomass, or a mix of biomass and fossil fuels, pulp mills for paper production, lime kilns for cement production, and refineries producing biofuels through fermentation, ethanol, or gasification, biogas, of biomass. BECS enables carbon removal because biomass absorbs CO2 as it grows, and this CO2 is not re-released when it is burned. Instead, it is captured and injected into deep geological formations, removing it from the natural carbon cycle. BECS is one of the most mature carbon removal options. There are a number of BCCS facilities operating around the world today, capturing CO2 from industrial processes, for example, ethanol production and biomass-based power generation. In the United States, for instance, the Illinois Industrial Carbon Capture and Storage Project is capturing up to 1 million tons of CO2 from a bioethanol facility each year and storing it in a dedicated geological site. In the United Kingdom, Drax has begun a pilot project to capture CO2 from its biomass-fueled power plant. If the project is successful, it could become the world's first negative emissions power plant. In some cases, BCCS can offer a relatively low-cost opportunity for the deployment of carbon capture and storage. This includes the production of bioethanol, where the CO2 capture costs can be as low as $25 per ton of CO2. At the same time, BCCS faces deployment challenges related to the availability of sustainable biomass and the need for infrastructure to transport and store CO2, which is lacking in most regions of the world. Direct air capture. Direct air capture can enable carbon removal in which CO2 captured from the atmosphere is permanently stored. The captured CO2 can also be sold for use, for example, in food and beverage production or for blending with low-carbon hydrogen to make synthetic fuels. But in most cases, the captured CO2 that is used is re-released into the atmosphere, such as when the fuel is burned. In these cases, use of the captured CO2 could still generate climate benefits, particularly where synthetic fuels are replacing conventional fossil fuels, for example. But this would not result in negative emissions. Due to the low concentration of CO2 in the atmosphere, direct air capture technologies are currently more energy intensive and expensive than other carbon capture applications, which draw off more concentrated CO2 from industrial facilities or power plants. Cost estimates in academic literature range between about $95 and $230 per ton of CO2 from direct air capture, with the lower end reflecting cost targets for future large-scale deployment. Today, more than 10 direct air capture plants are operating in Europe, the United States, and Canada. Most of these plants are small and sell the captured CO2 for use, for carbonating drinks, for example. However, the first large-scale direct air capture plant is now being developed in the United States by a partnership between Carbon Engineering and Occidental Petroleum. The plant will capture up to 1 million tons of CO2 each year for use in enhanced oil recovery and could become operational as early as 2023. In Iceland, the Carbfix project is capturing CO2 from the atmosphere for injection and storage in basalt rock formations. Carbon removal can be part of transitions to net zero and beyond. In its recent announcement, Microsoft said it is establishing a $1 billion climate innovation fund to accelerate the global development of carbon reduction, capture, and removal technologies. This could provide a much-needed boost for emerging carbon removal technologies, which will be important for meeting not only Microsoft's ambitious carbon negative pledge, but also broader climate goals.